Okay, so we're looking at FSM timing, and I'm going to do the problem that I had on exam 3 from fall 2011. So we've got this FSM circuit diagram right here, and here the first part says, based on the timing values given in table 1, circle the components in figure 2 that are part of the critical path. So the critical path means the longest path from the input to the output in terms of time, not necessarily in terms of the number of gates, but rather in terms of time, because some gates can take longer to get through than others. We're assuming the X1 input is stable, and the output Z1 drives the circuit not sensitive to the maximum clock frequency. So right away, when we're doing these calculations, we can forget about all this logic. And we also don't need to worry about X1 changing. So here, this inverter is not going to play any role in our calculation because its X1 is stable, which means the output of the inverter is also stable. Alright, so to first determine the critical path, we need to figure out the longest path from input to output. So you can see here there's delays given for different gates. The inverter is 2 nanoseconds. So I'm going to get a 2 for this guy. This one we're not going to worry about because X1 is stable. Then we have a 2 input OR gate. Has 4 nanoseconds. So 2 input ORs have 4. I'm going to write those here. Or I guess those are actually XORs. Sorry about that. 2 input OR gate. Do we have any of those? Oh, there it is. This is the 2 input OR gate. Let me go ahead and delete that. 2 input OR gate is this one. That has a propagation delay of 4. Then we have the 2 input XOR or XOR gate is 7. So these are all 7. Then we have the 2 input AND gate, which is 4. So these are 4. 2 input AND is a 4. And then we have the 3 input OR, which is a 5. Okay, so the longest path is going to be, let's see, we've got a long path here. We have a 2 plus a 4 plus a 5, which is going to be 6 plus 5, which is 11. So that's one contender. We also have here a 7 plus a 5. So that is going to be longer. That's 12. Do we have anything longer than 12? No. So, okay, we're going to have to go through this gate, and through this flip-flop. That's going to give us our longest delay through the circuit. Alright, so now that we know that, we're going to determine the maximum clock frequency for the circuit. For this problem, add a safety margin that is 10% of the minimum clock period based on the timing values. No need to use a clock calculator, just leave your final frequency number as an equation. Alright, so now we want to figure out what our Tmin is. So Tmin is going to be equal to T next state, because I'll put T next state, plus T setup, plus, now here we look at whether the propagation time or the hold time is longer. So because the propagation time is longer, we're going to use that. So T flip-flop PD plus our safety margin. But we don't know what it is yet, so we're not going to add that in. So our T next state, which we already figured out, the longest path was 12 nanoseconds. Our T setup time was 6, and our T prop delay is 12. So this is going to give us a Tmin of 30 nanoseconds. Now we still have to add in the 10% safety margin. So safety margin, T safety margin, or it was being called T slop, is equal to 30, or Tmin, times 10%, so times 0.1. So it's going to be 30 times 0.1, which is equal to 3. 10% of 30 is 3. So now our Tmin total is going to be, I guess I'll call this Tmin 1. Tmin is going to be Tmin 1 plus T slop, which is going to be 30 plus 3. So our maximum clock frequency, F max, is equal to 1 over T min. So this is equal to 1 over 33 nanoseconds, which I said here you don't need to use a calculator, just leave this answer. So your frequency is 1 over 33 nanoseconds. And that there gives you the maximum clock frequency that you can have to make sure the output of this circuit or the circuit operates as you expect it to. So the last part of this question said, if you want your maximum clock frequency to have a 33.3% duty cycle, or rather a third of the time high, for how long is the clock high each period? Please provide the exact number. Alright, so if our T min was 33, the duty cycle T high over T min is equal to over T, which is T min, is equal to the duty cycle. So we're going to have 33 and a third, or 33 and a third percent is 1/3. It's going to be equal to T high over T min. So T min over 3, T min was 33, 33 over 3 is going to be 11. So T high is equal to 11 nanoseconds. Sorry, this got a little messy. So basically you were trying to get a duty cycle to say you're a third of the time high. Since the period is 33, it's going to be a third of that, which is 11.